Morning. So here we are again. I decided to take a break from my garage, the low quality whiteboard therein. My wife has asked my stepdaughter to see if she wants to. We've got some blackboard paint in the house somewhere. That's that you can paint a wall and turn it into a blackboard. My wife's asked my stepdaughter if she would like to have an afternoon project where she paints over that whiteboard with blackboard paint, giving me a chance to have a better writing surface at home. Meanwhile, I decided to come back into campus, which is pretty abandoned right now. There are a handful of people around, mostly contractors still at work on the buildings that are undergoing renovation. For the most part, the academic buildings, though, are pretty empty, so I'm standing here in the Laurel Forum, Carpen Room 139, bringing you section 5.5. A little bit more practice with recursion and an opportunity to see some sequences at work, some important sequences. So we're going to talk about three particular sequences today. And I don't think any of the examples I'm going to do with you in just a moment here involve induction directly. But there are some sequences, in particular recursive sequences, give us an opportunity very often to prove some things by induction. And you'll actually see that at work in the exercises for this section 5.5, which are due not this coming Friday, which is Friday, April 3rd, but Friday, April 10th. You'll also see them in the second exam, which I've just written and will have already posted on the class Moodle site. So if you want to take a sneak peek at the exam, it's not due for a while yet. It's due on April 17th, so it's a ways to go yet. But you can take a look at that and start work with that on that at any time. So with no further ado, though, let's talk a little bit about some sequences. Remember, a sequence is really just a list of numbers from back in section 5.1. It's a list of numbers where order does matter, so you want to keep them in the order that they appeared. So it's different from a set in that regard. It's also different from a set in the regard that the terms of a sequence can repeat one another. So it's possible, and we'll see an example in a little while here, that a sequence, that a sequence has terms that actually may repeat. One sequence that your textbook mentions, again, this is section 5.5, talking about recursive sequences. One sequence that your textbook mentions is a collection of numbers called the Catalan numbers. Catalan numbers are given, the definition of them that's given in the text is this, C sub n, the nth Catalan number, is given by the formula 1 over n plus 1 times 2n choose n. Remember, this is that binomial coefficient notation, which we read as 2n, in this case 2n choose n, the number of ways of choosing n elements from among 2n possibilities. And this expands to 2n factorial divided by n factorial. Remember, we take the top factorial, divide by the bottom factorial, times the top minus the bottom factorial. And of course, in this case, that simplifies a little bit. And we have 2n factorial divided by n factorial. 2n minus n is again n. So we really have n factorial squared over there, if you want to write it like that. So this is the definition of the Catalan numbers, and as your textbook talks about, these numbers show up in a lot of counting problems if you're trying to enumerate the number of possibilities of something. There's a field of math called combinatorics, which is essentially the study of counting possibilities, counting combinations, counting different ways of different events occurring. Very useful if you're trying to figure out the probability of a certain event occurring, because you need to know how often it occurs. So Catalan number has this definition, but one of the things that makes it really interesting is one of the exercises that we'll do together is to show that it can be defined recursively. And what I mean by recursive, or a recurrence relation, recursive definition is one in which each term, or recursive sequence, is one in which each term of the sequence is defined in terms of previous ones in some fashion. And the equation that gives that recursive relationship is called a recurrence relation or a recurrence equation. Catalan numbers, even though they have this closed formula here, that gives you explicitly what the value is, can also be given the following recursive definition. So we can show that for all k greater than or equal to 1, the kth Catalan number is actually given in terms of the previous Catalan number using this formula. You take the previous one, the k minus first term, and you multiply by 4k minus 2 over k plus 1. This looks like kind of an odd formula, but we'll see how it works in tandem with this binomial coefficient to give us this recurrence formula. And again, this is a recursive definition or a recurrence relation that defines ck in terms of ck minus 1. The easiest way to work this one out, as we'll see with a lot of recurrence relations, is just to take this piece of the formula and expand it. Just play with it as much as we can to get it to look like this. And what we'll see at the end is that these two really are the same formula. They just expressed in different ways to begin with. So let's go ahead and start with this right-hand side. By the way, I had a couple of folks asking about the abbreviation LHS and RHS. And really that's just left-hand side, right-hand side. If we have an equation that has a left and a right-hand side with an equals in the middle, that's just notation, just abbreviation because I'm lazy. All right, so let's start with this right-hand side. The goal to prove that the right-hand side ends up equaling the left-hand side. And all I'm going to do is expand. The first thing is to replace this formula, ck minus 1, with the formula we know holds true for ck minus 1. So we've got the 4 k minus 2 over k plus 1. And now the formula for ck minus 1 is just this formula with n replaced by k minus 1. So if I'm really careful about where the n's are, I get this. And I'm going to get this LHS out of the way there. All right. And now the next step is to do a little simplification and to expand this using the definition of binomial coefficients. So we get 4k minus 2 over k plus 1. We have this term here simplifying to 1 over, well, k minus 1 plus 1 is just 1 over k. And then finally, we expand, just do a little bit of algebra as well, using the definition right here of binomial coefficients. I get a 2k minus 2, I just distributed that 2, factorial, divided by k minus 1, factorial, times, see here this is 2n minus n, but another way of writing that was just n factorial. But in this case, of course, it's going to be k minus 1 factorial. So I get a second k minus 1 factorial there. Okay, so far so good. Now I'm just going to do a little bit of rearranging here. Let's see what I want to do. In the top, what I'm going to do is I'm actually going to factor a 2 out of this. And you might see when I factor that 2 out why I do that, because now factoring the 2 out makes that look a lot more like this. Not quite, but pretty close. I'm going to collapse all these because we're just multiplying fractions, so I can put all the numerators together. I factor the 2 out of there, times 1, times this. And then in the bottom, I get a k plus 1, putting all the numerators together, times k, times 2 of those k minus 1 factorials. All right, we're getting there. Now, next thing I'm going to do, this might look a little strange. Let's see. Well, what else can I do here? Notice k minus 2 factorial times k minus 1. 2k minus 1. 2k minus 2 factorial times 2k minus 1. This would be the next term after 2k minus 2 if I wanted to extend this factorial one more step. In other words, I can make that 2k minus 1 factorial by just smushing this term into this one, because this term has all of the product of all the natural numbers below 2k minus 2. Let's just extend that by one more term. Same thing down here. If I take, let's see, do I want to do, actually, I'm not going to take all, I'm not going to put the k plus 1 in there. I'm going to put the k with the k minus 1 right there. The reason I do that is because in the same fashion, k minus 1 factorial has all the terms down to 1. If I put an extra term of k on there, I get k factorial instead of k minus 1 factorial. That still doesn't change that last k minus 1 factorial, however. That's just what it is. We're starting to see this left-hand side. Let's see, what I want to say. We're starting to see this appear here, right? The left-hand side of this equation is simply ck. And as part of that formula, we want to see 1 over k plus 1. Well, we have a k plus 1 in the denominator now, so our suspicion is that that is going to be a part off on its own. And we're still not quite at this binomial coefficient here, because what we'd really like to see is 2k factorial over k factorial times k factorial. Well, we've got a k factorial in the bottom, but we don't quite have a 2k factorial in the top. So what I'm going to do is a funny little trick where I multiply the top and the bottom, by an extra k. So I multiplied the top by an extra k, and I put another k in the bottom, just to make sure that we didn't change anything. If you multiply by a k and divide by a k, you get the same thing as what you started with, right? It's like multiplying by 1. But putting that extra k in the top means now I have 2k times 2k minus 1 factorial. Kind of like over here where I smushed the 2k minus 1 into the 2k minus 2 factorial. This whole top now just becomes 2k factorial. And this k can be smushed into that k minus 1 factorial to get k factorial in the bottom. So what we have, getting down to the bottom here, but we're almost done, is 2k factorial divided by k plus 1 times k factorial twice, k factorial squared. And if I pull the 1 over k plus 1 off on its own, let me just do this in 2 more steps. I pull the 1 over k plus 1 off on its own, then what I have left over is just 2k, choose k, and I end up with the left-hand side. 1 over k plus 1 times 2k choose k is the k Catalan number. And so starting with the right-hand side here, we were able to work this formula out until it became the left-hand side, which showed that this equation really does hold. We have a recurrence relation, or a recursive way of defining the Catalan numbers. So this wasn't, we've been talking about induction a lot, so it's really tempting whenever you see a statement about all natural numbers to assume that induction is the only way to go. In this case, we were able to do it directly. There's no induction involved here. Just like in the case we'll see in just a moment, there's no induction involved in the next one either. So make sure you pause the video right here and take a moment to make sure you understand this computation. And it might not hurt to look at some of the problems that are assigned for this particular section, section 5.5, to see if there are any like this that you can handle at this point. When you're done with that, go ahead and unpause, and we'll go on with another example, one that is a little more standard. The Fibonacci numbers, or the Fibonacci sequence. This is a famous sequence that was first described almost 1,000 years ago by an Italian mathematician who was hoping to understand population growth without using an exponential model. The idea of using exponential models as population growth would not come along for some time. What he was doing was trying to figure out a discrete way to do this, with the idea that if you had one pair of rabbits to start with, and they took a month to grow sexually mature so that they would give rise to another pair of rabbits at each time step thereafter, you would have one pair of rabbits to begin with. After 1 month's time, you would still have one pair of rabbits.
And after the next month, and all subsequent months, the number of pairs you would have, the number of pairs of rabbits you would have in your population would be found by taking the number that were present at the previous step added to the number that were present before that. Essentially what this is doing is it's saying that you have this many rabbits at the previous step and this many that are sexually active at that point, 1 month later. So it's like a lag time of sexual maturity. And what that means is you have all the previous rabbits plus a new pair of rabbits for each pair that had reached sexual maturity. So this is like an old-fashioned population dynamics problem. It actually, even though it's about 1,000 years old or so, it has since been shown to show up. The Fibonacci sequence has been shown to show up in so many different applications that there is a quarterly mathematical journal, it comes out 4 times a year, devoted entirely to problems involving the Fibonacci numbers or applications of the Fibonacci numbers. This too, unlike the Catalan numbers that we described on the other side, sometimes you can define the Catalan numbers, or sometimes you'll see the definition given in terms of the recursive formula. We had a closed formula that was given over here, and we found a recursive formula. Generally speaking, the Fibonacci numbers, the Fibonacci sequence, is defined by this recursive formula. This is almost always the way that it's defined. There is a closed formula for it, and it's not super hard to derive. If you take a course on linear algebra, you'll have all the tools that are necessary. So it's a 2nd or 3rd year math major problem to determine the closed form for the Fibonacci sequence. It's not hard, but it's beyond the scope of our course. Just for practice, we can figure out the first, let's just figure out the first several terms of the Fibonacci sequence. We're given the 2 terms to begin with, 1 and 1. And then the recursive formula kicks in after the 2nd term, or at the 2nd term. So at k equals 2, we see that we have f sub 2 minus 1 is f sub 1, plus f sub 2 minus 2 is 0. So we look at the previous 2 terms and we add them together. For k equals 3, same deal. We add, to find the 3rd term, we add the 2nd and the 1st. So 2 plus 1 is 3. For the 4th term, or the 5th actually, but the term number 4, we add the 3rd and the 2nd. And so forth. We can go through and to our heart's content. On the 2nd exam, I actually asked you a harder question about the Fibonacci numbers. We'll do a pretty easy one in a moment here. But there is a problem I'm asking you in the 2nd exam to prove using strong induction. So make sure you go back to section 5.4 and understand strong induction before you get on the exam. So here's the question that I'd like to pose, and we'll answer together here. Can we show, or the answer is yes, we can show it. So here's what I want you to do. Prove this particular recurrence, or this particular identity, rather. Make sure I get it right, otherwise it's going to be pretty hard to prove. Let's see if we can prove this particular identity about the Fibonacci numbers. And it turns out that there are hundreds of different interesting relationships between the Fibonacci numbers. And this is just one of them. So if you take the difference of squares of successive Fibonacci numbers, you get this formula that relates not just those 2 terms that we started with, fk and fk minus 1, but relates them to fk plus 1. Now, it takes a lot of practice to see the best way or the quickest way to prove formulas like this, but I'm gonna give us a little educated guess as to the most efficient way to do this. There are multiple ways to do this. I just want you to be clear, about that. But the way that I'm going to suggest to do this is to, because both sides involve k and k minus 1, we might be best off just trying to get rid of stuff that doesn't have a k or a k minus 1 in it. So for instance, k plus 1, you can always go back 2 steps using the recurrence relation. In other words, if I had a plus 1 here, let me do this in a different color. If I had a plus 1 here, I hope that red is showing up pretty well. That would be like adding plus 1 to each of these 2, and we'd see we would have f sub k plus 1 is f sub k, well, minus 1 plus 1 is just f sub k, plus f sub k minus 2 plus 1 is f sub k minus 1. So we're able to replace f sub k plus 1 with f sub k plus f sub k minus 1. So let's do the same thing we did the last time and just start with that right-hand side, replacing f sub k plus 1 with its recurrence formula. So the right-hand side is f sub k. Now I get f sub k plus 1 is f sub k plus f sub k minus 1 minus f sub k minus 1 times the same formula coming from that recurrence relation. Same formula for f sub k plus 1. Now it's just algebra. Let's just multiply this out. We get f sub k squared, right, f sub k times itself, plus f sub k times f sub k minus 1, minus f sub k minus 1 times f sub k, minus, making sure we distribute that minus sign, f sub k minus 1 times f sub k minus 1. Well, notice that these two cross terms, even though they're written in a different order, because multiplication is commutative, it doesn't matter which order we multiply them. One of them has a plus, one of them has a minus, so those cancel out. And all we get is that f sub k squared to start with, minus f sub k minus 1 times itself. That is just the left-hand side, and that is what we wanted. So that was a pretty easy computation. Much like the first one, it was just a direct computation, no induction involved. Again, not every statement involving the natural numbers is most easily proven by induction. Direct computation starting with the right-hand side and ending with the left-hand side. You could have done work, there are other ways to do this problem. You could have used the recurrence formula to replace other pieces of this equation, but I think this is the simplest because it involves the least manipulation. One more example of a recursively defined sequence that has a number of different applications, including also population dynamics, including, unfortunately, the current spread of coronavirus, but also financial applications, namely banking, computing compound interest on loans. I'm going to stick with the notation that your textbook uses just to be consistent. The idea behind compound interest is the following. Suppose we have an amount, a sub, again, let me just make it consistent here. A sub k, an amount in an account at time k, and each time step we accrue a percentage interest I of this amount. And what that means is, the more we have in the account, the greater the percentage interest, right? Interest expressed as a decimal. So if we express the percentage interest as a decimal, the more we have in the account, the greater will be given as interest, right? Some amount I times the amount in the account. So at the next time step, a sub k plus 1, we have the original amount plus some percentage times the original amount. And of course, since a sub k appears in both of these, appears in both of the terms on that right-hand side, we can just factor the a sub k out times this 1 plus I. So this 1 plus I is the principal term plus the interest term. And that gives us a formula for compound interest. But we can go a little bit further than that. The last computation I want to do is just to show you that, well, using this, iterating this formula gives us a closed form for expressing the amount in an account at any given time, not just in terms of the previous time step, but time steps before that. So, just to make the indices work a little nicer, I'm going to start with AK. But what we just showed is that the amount AK is 1 plus I times the amount in the previous time step, AK minus 1. Well, AK minus 1 itself is the amount at the time step previous to that times 1 plus I, which is 1 plus I times AK minus 2. And I'm just going to rewrite that as 1 plus I squared times AK minus 2. But there's nothing special about K minus 2. If we use the same recursive formula, I can go one time step further back and introduce another 1 plus I. So 3 time steps back, I have 3 terms 1 plus I, or 1 plus I cubed. And so forth. The same argument shows that 4 time steps back, I need to multiply by 1 plus I to the 4th, and so forth. I can go any number of steps back. Let's say j steps back, and just introduce 1 plus I to the j in front of it. So I can find the current amount, a sub k, in terms of any previous time step if I just multiply by the right power of 1 plus I to the j. If I want to write this as, if I'm more interested in the time step that I'm starting with, I can call this n, for instance. If I say I want n to be k minus j, because here, right now, it's written more in terms of this exponent than it is this time step. But if I want to write in terms of a single time step n, we'll let n equal k minus j, and then we can solve for j to figure out what that has to be. So if I add j to both sides and I subtract n, I see that j is equal to k minus n. So this gives us an alternate formula. A sub k can be written as 1 plus I to the k minus n times a sub n. And that formula is sometimes more handy because this tells us the current amount based on some fixed time step earlier. So for example, if that's not coronavirus, by the way, I've got seasonal allergies. For example, if a sub 0 is $100 and interest is compounded monthly at 5% per month, our initial amount of 100 becomes what after a year? Let's see. After a year, we've gone 12 months later, compounding at 5% interest means 1 plus 0.05, and then k minus n will be 12 minus 0 times a0. Well, it's 1.05 to the 12th times 100, and I just plug this into a calculator just to spare us the computations. This works out to be about $179.59. That's a pretty generous interest rate, but it does show that even with a fairly modest interest rate, you get pretty good growth if the compounding is done pretty frequently. Now, unfortunately, what we're seeing with the spread of the COVID virus is similar. We have a certain amount of cases that give rise to a percentage increase in the cases per day or per week, depending on the time step that you want to use. What we're seeing right now is exponential growth, because this exponent is what governs the growth in this function. So exponential growth in the case of compound interest, or exponential growth in the case of the spread of a virus or the spread of any population. But right now, the one that's most prevalent on our minds is COVID. So I hope this helps you understand not just compound interest, which again is a recurrence, is expressible using a recurrence formula, recurrence relation, as a recursively defined sequence. But also, as we had on the other side, the Catalan numbers, as I erased here, the Fibonacci sequence. These are all recursively defined sequences that give rise to time step information, discrete information in terms of previous steps. So that should do it for section 5.5. Again, make sure you do the problems for this section. Make sure you do the quiz. I'll post a quiz for this section on Moodle as well. And you should be able to get started with most of the problems from the exam number 2, which is, again, not due until April 17th, so there's some time off on that one. But it is already available on Moodle, so take a look at it. And as always, please let me know if you have any questions. Please let me know if there's anything I can do to support you. We're all in this together. I've heard from a lot of you, and I know many of you are safe and stable, but please stay that way. Stay safe, stay stable, stay in touch. Let me know if you need anything, and I'll see you soon.